These are the last notes for the whole organic section, and these last notes unfortunately involve a lot of memorization. None of this stuff has a chart or a table for you to reference in your reference tables, so you have to memorize these. All right, organic reactions usually react, I think we've mentioned this before, they're really slow. And they often involve only the functional groups and also sometimes the double or triple bonds. And that's because those bonds are not as stable as the bonds between carbon and hydrogen. The bonds between carbon and hydrogen are almost nonpolar because their electronegativities are so close. It's a very stable bond. So the functional groups and the double and triple bonds are actually more susceptible to reactions. So all of these that we're going to talk about involve those things. So the first one we're going to talk about is an addition reaction, and this only happens in unsaturated compounds. Unsaturated means that it has a double or a triple bond, which means typically it's an alkene or an alkyne. We call them unsaturated because they could have more hydrogens, except that they have that double and triple bond, so they aren't fully saturated. So alkenes and alkynes do this. This is split into two different types of addition reaction. You can imagine if it's a hydrogenation reaction that you're going to be adding hydrogen, and if it's a halogenation reaction, you're going to be adding halogen. What's special about this is that it happens across a double or a triple bond. So in hydrogenation, you have hydrogen added across a double or a triple bond. So when we look here at our 2-pentene, it's this double bond that's actually going to break when we add hydrogen to it. If you've ever heard of hydrogenated oils, what they've done is they've taken an unsaturated oil, meaning it has double or triple bonds in, well, they're double bonds, they aren't triple, but they have a double bond in that fatty acid chain, and when they add the hydrogen across it, they break these bonds, making it a saturated fatty acid, which tastes better and also are typically solid at room temperature, so that's why they would do that. So what you're going to end up doing is this hydrogen, the H2, is going to be added across this bond, putting a hydrogen on each of these carbons and making the bond between them a single bond. So you're going to end up with pentane when you're all done. So normally we don't write in the hydrogens. I'm going to write in the two we added so you can see. So we actually broke one of these two bonds so that these two carbons could pick up the two hydrogens from H2. And halogenation, it's the same thing, except it's a halogen, so fluorine, bromine, chlorine, iodine, that's added across that double or triple bond. So here is, again, 2-pentene. And we're going to add, doesn't really matter which one we pick, I'm going to pick chlorine. We're going to add Cl2. So once again, one of these bonds in this double bond is going to break, allowing each of these carbons to pick up a chlorine. So now we have a chlorine here and a chlorine here, and all the rest are still hydrogens. And we should probably name this. This would be 2,3-dichloropentane. The next type of reaction we're going to talk about is polymerization, or joining of small subunits into big ones. So we're going to join monomers, that's the small subunits, and we're going to make them into a much longer chain, which we call polymers. We talked about this in Regents Biology or Living Environment when you talked about making proteins. Because what happens is those small monomers or small subunits called amino acids are linked together into longer chains called polypeptides, which then are put together into proteins. So we're going to talk about two different types of polymerization. The first one is addition polymerization, and just like when we talked about addition in the last reaction type, it's got to involve a double or a triple bond. So we're going to be joining unsaturated monomers. So the small subunits have to have a double or a triple bond in it. So this is actually ethene, and what you're going to end up doing, you have N of them, that's some number of them. And what you end up doing when you break that bond is being able to link to lots of chains of ethanes. So this would continue in both directions. And to show that that's the case, we put parentheses, and now we put the N as a subscript. So pretty much if you see an N, it's going to be polymerization. And if it involves a double bond, it's going to be addition polymerization. Condensation polymerization, when you think of condensation, I hope you think of water. And really what we're doing is we're removing water to join the monomers. So this one, typically, you wouldn't have to come up with the product. You would have to recognize that that's what's happening. I'm going to show you, though, because I want you to see how it happens. With these, we have 1,2-ethanediol right here and right here. And what will happen is an H from one and an OH from the other will come together to form one of our products, which is water, H2O. And then the second bond on this oxygen is actually going to link up and make that last bond on that carbon. So you're going to end up with, and this is going to get a little complicated, this is the oxygen that we left here. All I've drawn is this part of this chain. And that's going to link to the C and the OH that still exists on this side. And then the rest were all hydrogens like so. And this could continue and continue and continue. So a lot of times you're going to see this in parentheses. You might see an N in this as well. Now, we should talk about when we use this kind of polymerization, both the addition and the condensation. So let me mention that. They do like to ask about it. When we do addition polymerization, that's this one up here, a lot of times we're doing that to make synthetic things like polyethylene. They actually have polyethylene in the lunchroom. That's the plastic containers for the salad. Polystyrene, which you may know as styrofoam. Acrylic, a lot of woven fabrics are made out of acrylic. It's a very durable fiber. PVC, that's what like sewer pipes and stuff in a house are made out of, that white tube that you might see if you go in the basement. Those are all examples of addition polymerization products. For condensation polymerization, we actually can break this into natural reactions because this does happen naturally. And also we can talk about synthetic ones. Some of the natural ones you've already covered in your biology course. They would be like making proteins. That's actually a condensation polymerization reaction. Also making starches. And more specifically in plants when they make cellulose. Cellulose is a very, very hardy product. It's actually what's making the xylem and phloem in plants, or you might think of it as the stringy stuff in celery. We actually can't even digest that, but that makes it even better thing for you to eat. Synthetic examples of condensation polymerization would be silicone, like silicone caulk. That's synthetic. Polyester, also a really durable fiber for making fabrics and whatnot. Nylon, I think pantyhose, and some plastics. All right, on to the back side. Substitution happens when you have a saturated hydrocarbon. And the reason why we call it substitution is because a hydrogen or one or more hydrogens is replaced. And what you're going to see that makes this different, there's a couple of things that make this different from addition reactions, is first, it's saturated. There's no double or triple bonds. And you'll also see that there's two products, because when you replace something, the H is going to come off and need to form a new compound. So there's a couple of different ways you can make this product. Some of the product will look like this, where you have a single bromine on there, and that bromine replaced this hydrogen. So that hydrogen needs to go somewhere. Hydrogen will never be by itself, though. It needs to make a bond. So if you're only putting one bromine on here, we started with two, one of your products is going to be HBr. So if you have another option as a product, if you replaced two of the H's, so let's say you put a Br here as well, you would have pulled off two of the H's, so your other product, instead of being HBr, would be H2. So in fact, when you do that reaction, you're going to get both things. Or you might have some of your product with two Brs, one here, or one on here and one on here. You're going to have a lot of different products, so there's more than one correct answer, but you need to make sure that you show what happens to the hydrogen that was substituted. All right, next reaction, oxidation, you might know as combustion. Essentially, it's burning things. It's a reaction that happens in your body all the time at a really, really slow rate. It's called respiration, which you learned about in biology as well. Essentially, you're going to have some organic molecule and oxygen, and you're going to end up making CO2 and water. So you're going to actually produce some water. So here we have an organic molecule that happens to be ethane and oxygen, and what we're going to end up making is CO2 and water every time. So the thing you're going to be looking for is oxygen. It's the only reaction you need to know where it involves oxygen, and the products are always CO2 and water. If you're bothered that this isn't balanced, this would actually be 4 and this would be 6. Next one, fermentation, one of my favorite reactions. We have some sort of sugar plus yeast in some way. They may, instead of saying yeast, they may actually put the enzyme that does fermentation in the yeast. It's called zymase. And it always produces CO2 and ethanol. So in our example down here, we have glucose and yeast, and I just wrote zymase down. You should include that so you know. Usually they don't give you both. They'll give you one or the other, but you need to recognize both. And the products are going to be CO2 and ethanol. I'm going to draw out the structural formula, but they could just write ethanol like I have it in the line up here. All right, next one is esterification. As you can imagine, we're going to make an ester. When we make an ester, it's the result of having an organic acid react with an alcohol. And if you haven't done that yet in lab, you will be doing it. And you actually make an ester and water. So one of the products is going to be water, just like the condensation, polymerization reactions. So here's what happens, and it's kind of confusing, but essentially what happens is you're going to pull off water, just like we did in condensation, polymerization. In this case, and they've actually done studies, they've labeled the oxygens to know which one it is that's actually used to produce the water in the reaction, and it's actually like this. So the OH is going to come off of the organic acid, and the H is going to come off of the alcohol. This fourth bond then that carbon has left is actually going to bond to the other bond on that oxygen. Remember, oxygen always needs to make two. So you're going to end up with one of your products is going to be water, and the other one is going to be this ester. And we're going to build that from what we've got here. So in my organic acid, I had this. And then that fourth bond that used to be attached here to this OH is going to attach to this O. So that's where that O is. And then my two carbons from the rest of that alcohol. And it looks like this. And we would call this ethyl ethanoate. Last one, saponification. There's actually a little hint in there. If you unscramble those letters, it makes soap. So you have an ester or a fat and a super strong base. And you should recognize the strong bases. Usually it's either NaOH, which is lye, or KOH, potassium hydroxide. Those are super strong bases. And you're going to make soap, and one of the products will be an alcohol. So if you've ever seen the movie Fight Club, not that I'm suggesting you do, but he uses fat and lye, and he actually makes soap and alcohol, and he sells it to make money. So here's an example of a reaction you might see. You have NaOH and fat or oil, and it will make glycerol, which could be dangerous sometimes, and soap. Although if you treat it right, you can make it into glycerin, which is super good for hydrating your hands. And those are the reactions you need to memorize.